Dear students, you have already learned a little bit of average values and expectation values, so let us learn a little more today about the same topic. I told you that whenever we add up discrete values, say x1, x2, x3, and so on, we use the term summation. So, summation I goes from 1 to n. This gives the sum of these values, right? And in case you have to find the mean, the average of the same, you simply divide it by n. Summation I goes from 1 to n xi. This is equal to x bar, that is the average of the discrete values. But in case you add up certain continuous quantities, continuous I mean that for instance from 0 to 1 you can choose infinite number of values, say 0.01, 0.001, 0.0001, and so on. Therefore, in that case, this n tends to infinity. And whenever we divide this expression by infinity, this comes out to be 0. That means the conventional method of obtaining mean in case of discrete quantities does not work in case of a range of values which are continuous. So, we shift our understanding from this summation to integration. So, integration is actually used to add up quantities which fall in a continuous range. In addition to that, what we want to improve is that if we have to find the average, the expectation value over here, we introduce a new definition, and that is if f is any observable, by observable again I am reiterating that observable means any measurable physical quantity, say position, velocity, momentum, kinetic energy, total energy, angular momentum, and so on. And we know that with every observable, every measurable quantity in quantum mechanics, we have an operator associated with it. Now, in order to find the expectation value, which in the classical sense would have meant actually the mean value, the average value, here we call it the expectation value, it is written in this way. F is equal to integral psi star operator of f psi d top, where you have to remember that is FOP is the operator corresponding to the observable f, and you have to put this f in braces of this kind and not of any kind like this or this. No, you have to be very specific about notations, that expectation values are always put in the curly braces of this type. Now, as an example, let us again choose the particle in one-dimensional box whose expression, I mean wave function, is given by under root 2 by L sine of pi x by L. Now we are interested in the present case to find the expectation value of momentum. We want to find the expectation value of momentum for a particle in a one-dimensional box of length L. So let's do that. We know that expectation value momentum is given by integral. Look at this expression, will follow the same. For psi star, again I told you there is no complex quantity here, so there is no factor like iota and other things. So the complex conjugate and the quantity itself, the wave function itself, they are the same. So basically we have to write this twice. Under root 2 by L sine of pi x by L. For the operator, we'll write the operator for momentum, and now we have done it many times in our calculations, that is h cross by I tau by tau x. Again, we'll write the wave function psi, that is under root 2 by L sine of pi x by L dx. So let's try to simplify that. Again, we are taking our limits from 0 to L. Now, this under root 2 by L and under root 2 by L will come out. So that will be 2 by L. So this is integral 0 to L sine of pi x by L, and for this you will write differentiation of sine as cos of pi x by L, and then this factor pi by L will come into multiplication, and that we'll write here, right, dx. Now again we are getting a formula twice sine theta cos theta, that is equal to sine of 2 theta. So we are getting pi by L square integral 0 to L sine of 2 pi x by L dx. Now we again understand that this is equal to pi by L square. Integration of sine is minus cos, so cos of 2x by L, and then 2 pi x by L, and then the coefficient of x 2 pi L will come in the division, and the limits are from 0 to L. Now you understand that when we put x equal to L, we get cos of 2 pi. Cos of 2 pi is 1. And when we put L equal to 0, we get cos 0, that is again equal to 1. So 1 minus 1 is 0. This implies that expectation value of momentum is 0. So for a particle in one-dimensional box, what do we write? We say for a particle, the expectation value of momentum is 0. Similarly, you may be asked to find the expectation value of position, which you will be easy to calculate following the same procedure. Thank you.